We are told a story about the beginning. It's a powerful story. Nearly 14 billion years ago, everything we know, all the stars, all the planets, all the light, and even time itself burst forth from a single point of unimaginable density. We call it the Big Bang. It is the accepted origin of our cosmos. And yet, doesn't it feel incomplete? Doesn't it strike you as slightly rupture, beginning from absolute nothing, a creation ex nihilo? In our experience in every aspect of nature, we observe things don't come from nothing. They come from something else. The tree comes from a seed, the river flows from the rain, day follows night, summer follows winter. Our universe is defined by cycles, by repetition, by transformation. Why then should the universe itself be the one exception? Why must it have a day one before which there was nothing? This question, this deep dissatisfaction with an absolute beginning, isn't just a philosophical itch. It is the driving force behind one of the most profound and elegant ideas in cosmology. What if the Big Bang wasn't the beginning? What if it was just a beginning? This alternative idea is called the cyclical universe. In its simplest form, it suggests that our universe didn't just start, it restarted. Imagine the cosmos as a vast cosmic lung. For billions of years it inhales. This is the expansion we see today, the galaxies all rushing away from each other. But perhaps this expansion will not last forever. Perhaps gravity, the persistent, gentle pull of everything on everything else, will eventually win. The expansion will slow, stop, and then reverse. The universe will begin to contract, pulling all that scattered matter and energy back together. This isn't an end, it's the exhale. This contracting phase is often called the Big Crunch. As everything rushes back together, the universe becomes incredibly hot and dense, just like it was at the Big Bang. But instead of being an endpoint, a singularity of infinite density, it becomes a transition point. A big bounce. The universe doesn't crash into oblivion, it rebounds. The immense pressure of that collapse triggers a new expansion, a new Big Bang. Our universe, the one we are living in right now, would be just one pulse in an eternal sequence of expansion and contraction. This vision of an eternal repeating cosmos is not a modern invention. In fact, it is one of humanity's oldest ideas. Ancient Hindu cosmology speaks of yugas, vast ages that cycle upon one another. The universe in this view undergoes an endless cycle of creation and dissolution, a day and night of Brahma, where the cosmos manifests and then withdraws, only to manifest again. The Stoics of ancient Greece also conceived of a universe that would be destroyed by fire, an ekpyrosis, and then be born anew, perfectly repeating its own history, a concept they called palingenesis. These were philosophical attempts to grapple with eternity. They saw cycles in the heavens and seasons on Earth, and naturally assumed the cosmos must follow the same pattern. For centuries, these ideas remained in the realm of myth and philosophy. But in the 20th and 21st centuries, our most advanced theories of physics, first Einstein's general relativity, and now even stranger ideas like string theory, have brought this ancient intuition back into the laboratory of theoretical science. One of the most radical modern versions of this cyclical idea comes from the complex world of string theory. This theory proposes that our universe, with its 3 dimensions of space and 1 of time, is not all there is. It suggests our universe is a vast flat sheet, a brane, which is short for membrane floating in a higher dimensional space, the ekpyrotic model. A name borrowed from that ancient Greek idea of a fiery rebirth proposes that there is another brane, a parallel universe existing in this same higher dimension. For most of eternity, these 2 branes are cold, dark, and empty. They drift slowly toward each other. The Big Bang in this scenario was not a beginning from a single point. Instead, it was the cataclysmic collision of these 2 cosmic membranes. The impact is like a cosmic clap. The kinetic energy of this collision is transformed into the heat, the matter, and the radiation that fills our universe. This bang also pushes the 2 branes apart, starting the expansion we observe, but gravity is still pulling them back. Over trillions of years, they will cool, empty out, and inevitably drift back together, setting the stage for the next collision, the next fiery rebirth. The more classic cyclical model, however, doesn't require extra dimensions or colliding branes. It relies only on Albert Einstein's great theory of gravity general relativity. This theory describes the universe as a cosmic tug-of-war. On one side, you have the initial push of the Big Bang flinging everything outward. On the other side, you have gravity, the mutual attraction of all the matter in the universe, pulling everything back together. The fate of the universe in this model depends on a simple question: which one is stronger? Or more precisely, is there enough stuff in the universe for gravity to eventually win? If the density of matter and energy is high enough, gravity will act as a cosmic brake. The expansion will slow down over billions of years, eventually halt and then reverse. The universe will begin to fall back in on itself, galaxies rushing toward each other, faster and faster until the entire cosmos collapses into a big crunch. This scenario was a serious contender for decades. The appeal was its symmetry, a big bang to start, a big crunch to end, and from that end perhaps a new beginning could emerge. But there is a shadow that hangs over all these beautiful cyclical ideas. It is a fundamental law of physics, perhaps the most stubborn law we know, the second law of thermodynamics. This law states that in any closed system, the total amount of disorder, which scientists call entropy, can only increase over time. Think of it this way. It's easy to break an egg, increasing its disorder, but impossible to spontaneously reverse the process and put the broken egg back together. A hot cup of coffee always cools down, spreading its heat a form of energy into the room, increasing the overall disorder of the system. It never spontaneously gathers the heat back from the room to become hot again. The universe as a whole seems to be the ultimate closed system. As it expands, stars burn out, energy spreads thin, and the overall entropy increases. Here's the critical problem. If the universe collapses in a big crunch and then bounces into a new big bang, what happens to all that entropy? What happens to all the disorder created in the previous cycle? The second law demands that the entropy must be carried over. Each new cycle would have to start with more entropy than the one before it. The new universe would be slightly more disorganized, slightly larger, and would last slightly longer. If this cycle has been happening for eternity as the models propose, then after an infinite number of cycles, our current universe should be infinitely large, infinitely cold, and infinitely disordered. It should be a thin dead heat death of randomly drifting particles. But that is not what we see. We see a universe full of structure, of stars, of galaxies, of life. We see a universe that started in a state of incredibly low entropy, a highly ordered state. How can an eternal cyclical model explain this highly ordered beginning? This is the great entropy paradox, the central challenge that any cyclical theory must overcome. But what if that's not the end of the story? What if this long, slow fade into darkness isn't a final curtain, but just an intermission? This is where our story takes a fascinating turn away from a definitive end and into the realm of the eternal cycle. The biggest hurdle for any cyclical model, any idea of a universe that repeats, is a formidable law of physics: entropy. It's the universe's tendency toward disorder. Think of it as a one-way street. You can't unscramble an egg. You can't put the spilled milk back in the bottle perfectly. Once energy spreads out and disorder increases, you can't easily gather it all back up into a neat high-energy state. So if our universe expanded, cooled and died, and then somehow collapsed back on itself for another big bang, it should bring all that disorder back with it. Each new universe would be born older and more disordered than the last. After just a few cycles, the whole system would run down, unable to form stars or galaxies, and settle into a permanent lukewarm haze. The cycles wouldn't be able to continue forever, unless there's a way to reset the count. Some models, like the ekpyrotic model, a wonderful word that means conflagration or birth from fire, propose a radical solution. This idea comes from string theory, which suggests our universe is just one brain, like a giant three-dimensional sheet floating in a higher dimensional space. In this model, the Big Bang wasn't a start from nothing, but the result of our brain colliding with another. But what about the entropy? The model suggests that during the big crunch phase, as the universe contracts, the entropy doesn't just get squashed. It leaks away, possibly into these other higher dimensions we can't see. The universe essentially cleans house before the next cycle. It's a beautiful, if unproven, idea that the universe performs a deep cosmic reset, shedding its old disordered self so it can be born anew. Another brilliant mind, Roger Penrose, offers a different and perhaps even more profound perspective. He calls it conformal cyclic cosmology, or CCC. His idea doesn't require extra dimensions, just a mind-bending shift in perspective. He asks us to look at the very, very distant future, a future where all the black holes have evaporated, all matter has decayed, and only faint particles of light photons drift aimlessly through an endlessly expanding cold dark void. In this future, there is nothing left to measure scale. There are no rulers, no clocks. A massless photon doesn't even experience the passage of time. In such a universe, Penrose argues the concepts of size and time become meaningless. And when size becomes meaningless, the infinitely vast, cold, empty future of our universe looks mathematically identical to the infinitely dense, hot, tiny point of a Big Bang. Think about it this way. Infinity divided by anything is still infinity. An infinitely large universe and an infinitely small one become, in a strange mathematical sense, the same. Through a process called conformal scaling, a geometric resizing the end of our universe, our aeon becomes the perfect smooth starting point for the next. The vast empty cosmos becomes the singularity. The cold future becomes the hot past. Our end is the next universe's beginning. In this vision, there is no end at all, only a seamless transition from one aeon to the next, stretching backward and forward into infinity. Penrose even suggests we might be able to see echoes of the previous eon massive impacts or gravitational wave ripples imprinted faintly onto the cosmic microwave background, the afterglow of our own Big Bang. This brings us to a central theme in these new models, the bounce. The old story gave us a singularity, a point of infinite density and zero size, where all our laws of physics break down. It's a mathematical dead end, a sign that our theories are incomplete. The bounce replaces this singularity with a moment of transition. Instead of a universe born from an impossible point, the bounce suggests our universe emerged from the collapse of a previous one. Imagine a universe contracting, falling in on itself, getting smaller and smaller, hotter and hotter, but instead of crushing down to an infinitely small point, it hits a limit. It reaches a point of maximum density, and then with unimaginable force bounces back out, creating the explosive expansion we call the Big Bang. But what provides the spring? What stops the universe from collapsing completely? The answer may lie in the very fabric of space itself. A theory called loop quantum gravity, or LQC for its cosmological application, offers a stunning picture. It suggests that space and time are not smooth and continuous. If you could zoom in way down, past atoms, past quarks, you would find that space is made of discrete indivisible units, atoms of space-time. You cannot have half an atom of space. This quantized nature of geometry means there is a fundamental limit. You cannot crush the universe into a space smaller than this fundamental unit. As the contracting universe approaches this limit, gravity, which was pulling everything together, suddenly becomes incredibly repulsive. It pushes back. The universe doesn't hit a singularity, it hits a quantum bridge. The collapse halts and the rebound begins. The Big Bang is not a beginning, but a big bounce. This changes everything. If this is true, our universe is just one in a long, perhaps infinite series of cycles. Collapsing, bouncing, expanding over and over, it's a powerful philosophical shift. If the universe had a beginning, a Big Bang singularity, it demands a the before. It begs the question, what or who was the first cause, what set the universe in motion? But a bouncing cyclical universe doesn't need a first cause. It has no beginning, it has always been. It is self-sustaining. The question, what came before the Big Bang, is answered with the universe. This is the universe as the phoenix. The mythical bird that lives for 1,000 years is consumed in fire and is then reborn from its own ashes, new and young, to live again. It's an idea that resonates deep within us, an echo of the cycles we see all around us, the turning of the seasons, the rhythm of day and night, the pattern of life, death and rebirth. Perhaps our cosmos is the ultimate expression of this eternal cycle. Not a story with a beginning and an end, but an endless, timeless poem forever folding in on itself, forever bursting forth into new light. So we've been hovering around this moment, the Big Bang. We've been asking when it happened. But this obsession with when hides a much deeper question. When we ask when, we are assuming that time is a simple thing like a ruler that stretches back forever. We assume it's this constant universal clock ticking away in the background. But what if it's not? What if time isn't the ruler, but something that is created along with the universe? This shifts our entire perspective. We stop asking when the universe began and we start asking, what is time, especially at that very first moment? This leads us to a powerful idea, emergent time. Think about the property of wetness. You cannot take one single molecule of water and call it wet. Wetness isn't a property of a single molecule. It's a property that emerges only when you have billions and billions of water molecules all interacting together. It's a collective behavior. What if time is like that? What if time isn't a fundamental little grain of reality, but a large-scale property that emerges from the complex interactions of the entire universe in the super hot, super dense, chaotic foam of the very beginning? Maybe time as we know it, this steady, forward-flowing river, didn't even exist yet. The very concepts of before and after might have been meaningless. Only as the universe expanded, cooled, and became more organized did this property we call time emerge, separating itself from space and creating the arrow of cause and effect that now rules our lives. This is a profound thought. It means time is a physical, changeable, and created part of the cosmos. And this very idea is what allowed the great physicist Stephen Hawking to tackle the ultimate puzzle, the singularity. Hawking, like all physicists, was deeply troubled by that point of zero size and infinite density. In physics, infinity is not a real answer. It's a sign that your mathematics is broken. He wanted to find a way to describe the beginning of the universe that didn't break the laws of physics. To do this, he introduced one of the most famous and most misunderstood concepts in science: imaginary time. Now, imaginary doesn't mean make-believe. It's a specific mathematical term. In math, you have regular numbers like 1, 5, and 10, but you also have a special tool called an imaginary number. It's based on the square root of -1. It's just a trick, a special wrench that mathematicians and engineers use to solve very real problems that are otherwise impossible. In Einstein's equations of general relativity, time and space are not treated equally. Time has a minus sign in the equations, while the 3 dimensions of space, length, width, height all have plus signs. This minus sign is what makes time special. It's what separates the past from the future. It's also what creates the problem of the singularity. Hawking's genius was to use the imaginary number tool to mathematically rotate time. He turned that minus sign in the equation into a plus sign. By doing this, he mathematically transformed the dimension of time into a 4th dimension of space. Why would he do this? Because in this new 4-dimensional space, the singularity vanishes, the problem goes away. That sharp, violent point of infinite density where all the laws of physics collapse is smoothed out. It becomes a gentle curved surface like the cap of a sphere. The beginning is no longer a moment of infinite broken physics. It's just a part of the universe's geometry. This mathematical model led directly to his most beautiful and powerful idea, the no-boundary proposal. To understand this, Hawking gave us the perfect analogy. Imagine you're an explorer on the surface of the Earth. You decide to travel south as far as you can go. You keep going south, south, south until you finally reach the South Pole. Now you are standing exactly at the South Pole. I ask you, which way is south? You can't point. Any direction you step, any direction at all, is north. The very concept of south has disappeared at that point. The South Pole is the start of all the lines of longitude, but it is not an edge. The Earth doesn't end there. You haven't fallen off the side of the world. You're just at a special point on a smooth curved surface. Hawking's no-boundary proposal says that the universe is just like that. In his model using that imaginary time math, the universe is finite. It has a certain size just as the Earth's surface has a finite area. But like the Earth, it has no edge. It has no boundary. It is a complete closed, self-contained shape. And the Big Bang. The Big Bang is the South Pole. This completely changes how we think about the beginning. This brings us to the meaning of before the Big Bang. If the Big Bang is the South Pole of our universe's space-time, then what happens if we ask what came before the Big Bang? The question is meaningless. It is exactly the same as standing at the South Pole and asking what is south of the South Pole. Before is a concept that requires time. But in this model, time itself begins at that point just as all the norths begin at the pole. As you approach the Big Bang going back in time, the dimension of time itself would gradually fade, becoming just another direction in space. The rules of before and after would cease to apply. In this view, the universe didn't start at a moment in time. It wasn't that there was a dark, empty void, and then a bang. No, the universe and time itself simply is. It is a complete 4-dimensional shape that contains its own beginning. It doesn't need an outside cause. It doesn't need a spark to light the fuse because there is no fuse. There is no outside for a lighter to come from. The laws of physics, quantum mechanics, and gravity are sufficient to describe a universe that is self-contained. A universe that just exists without a creation event, without a boundary. This is perhaps the most profound and difficult idea in all of cosmology. It proposes a universe that is its own explanation. It is beautiful, elegant, and needs nothing beyond itself to be. It is a cosmos that is whole unto itself. Let's talk about the most fundamental thing we experience. More fundamental than the ground beneath our feet or the air we breathe. Let's talk about the tick-tock of the clock. We live our lives by it. We schedule, we wait, we remember, we anticipate. Time feels like a great cosmic river, carrying all of us downstream whether we like it or not. But what if it isn't? What if I told you that in the search for the true nature of reality, the river disappears? This is the strange and beautiful world of timeless physics. When physicists like Carlo Rovelli in his work on loop quantum gravity try to write the equations for the entire universe, they run into a fascinating problem. When you get down to the smallest possible scale, the Planck scale, far smaller than an atom, the t, the symbol for time simply vanishes from the mathematics. At this deepest level, the equations don't describe how things evolve in time. They just describe how things are relative to other things. There is no master clock. There is no flow. The universe at its core might just be a static, interwoven reality of events. What we think of as change is just the relationship between these different parts of the whole. So where does our clock come from? If the deep reality is timeless, why am I speaking now and why are you listening now? This leads to the idea of relational time. Think about how you actually measure time. You never just measure time. You measure one change against another. You know a minute has passed because you see the second hand move relative to the numbers on the clock face. You know a year has passed because the Earth has returned to its same position relative to the Sun. Time in this view is not an absolute flow. It is the relationship between events. It's the universe's internal bookkeeping. Time emerges from the interactions. It's not the stage on which the play happens, it's part of the play itself. But this creates a profound mystery. If the fundamental laws are timeless or at least symmetric, meaning they work the same forward as backward, why does our world only go one way? This is the arrow of time. The laws of physics for the most part don't care about direction. A video of two billiard balls colliding looks perfectly normal if you play it backward. You can't tell which way is correct, but a video of an egg falling and smashing on the floor, if you play that backward, you see a splatter of yolk and shell leap off the floor and assemble into a perfect unbroken egg. That is absurd. It never happens. Something powerful pushes our world from past to future. That something is called entropy. Entropy is a powerful concept. It's often called disorder, but it's more precise to call it the number of ways a system can be arranged. A clean, organized room has low entropy. There are only a few ways for it to be clean. A messy room has high entropy. There are thousands, even millions of ways for books and clothes to be scattered around. The second law of thermodynamics is perhaps the most unbreakable rule in the cosmos. In any closed system, entropy always increases. Things move from order to disorder. An unbroken egg is a low entropy state. All its molecules are in a very specific ordered arrangement. A smashed egg on the floor is a high entropy state. There are countless ways for the bits of shell and yolk to be splattered. The universe always moves from the low entropy unbroken state to the high entropy smashed state. This is the arrow of time. Time flows in the direction of increasing entropy. The only reason we have a past and a future, the only reason we remember one and not the other, is because the universe began in an incomprehensibly special state, a state of extremely low entropy. The Big Bang wasn't just a bang. It was a moment of perfect pristine order, a perfectly wound up cosmic clock. For the last 13.8 billion years, that clock has been unwinding. The universe has been moving from that perfect order toward greater and greater disorder. Stars burn fuel and radiate heat, spreading their energy. Galaxies drift apart. We are part of this process. We are born, we live, we process energy, and we return that energy to the universe in a more disordered state. This leads us to the most difficult philosophical question of all. If time itself is just a product of this unwinding, what caused the Big Bang? The word cause is broken here. Cause implies a before. How can anything happen before the beginning of time if the Big Bang is the origin of the arrow of time? Asking what caused, it is like asking what is north of the North Pole. The question itself might not make sense. This is the philosophy of timelessness. We must let go of our intuition. Perhaps the universe doesn't have a cause in the way a domino causes the next one to fall. Perhaps the universe simply is governed by a set of logical rules that require it to exist in this way. In this view, the universe isn't happening, it just is. Imagine the entire history of the cosmos from the Big Bang to its final cold end as a single four-dimensional object, a block universe. In this block, the past, the present, and the future all exist together, just as here and there exist in space. Our consciousness then is like a spotlight illuminating one slice of this block at a time. We experience a flow, a now that moves from past to future. But this is an illusion of our perspective. The other slices, the past and the future, are just as real. They are simply not in our spotlight now. The cause of the Big Bang in this framework isn't something that came before it. The cause might be the entire structure itself. The universe might be a self-consistent loop. The low entropy beginning is required by the high entropy end and vice versa. We are forced to trade our comfortable flowing river for a static frozen crystal. A universe that exists all at once, and we are just a pattern, a small complex eddy within that crystal experiencing our slice of reality convinced it is the only thing that is real. We have been staring at that single point, that singularity, for a long time. It's the traditional answer to, where did it all come from? It is a beginning that is so dense, so hot, so absolute that our laws of physics simply stop. General relativity, the law of the very large, gives us an answer that it cannot compute. But what if the answer isn't just found in the laws of the large? What if the origin of the everything, the cosmos itself, is governed by the laws of the very, very small? This brings us to a different and perhaps more profound idea of a beginning. It's an origin story that doesn't start with a point, but with a possibility. This is the idea of a quantum origin, a universe born from a quantum fluctuation. To understand this, we have to radically change our definition of nothing. In our everyday lives, nothing is an empty room, a vacuum. It is the absence of stuff. But in the strange and wonderful world of quantum mechanics, nothing is perhaps the busiest place in the universe. The true vacuum, what physicists call the quantum vacuum, is not empty. It is a simmering, chaotic sea of potential. One of the fundamental rules of this realm is the Heisenberg uncertainty principle. In simple terms, this principle states that you can never be perfectly certain about certain pairs of properties at the same time. For instance, you can't know a particle's exact position and its exact momentum simultaneously. This uncertainty also applies to energy and time. The universe at this microscopic level is allowed to borrow energy as long as it pays it back very, very quickly. Because of this rule, the empty vacuum is constantly borrowing tiny amounts of energy from the future, using it to create pairs of virtual particles, a particle and its antimatter twin. These pairs pop into existence, look around for a fraction of a second, and then collide, annihilating each other and paying back the energy they borrowed. This isn't just theory, we can measure the effects of this, it is real. So nothingness is actually a roiling, bubbling foam of these virtual particles appearing and disappearing. It is a state of pure jittery potential. Now imagine this quantum foam stretching not just through all of space, but through all of time, or perhaps in a state before time as we know it. This is a concept called eternal fluctuation. The nothingness is inherently unstable. It is always bubbling. Most of these bubbles of energy, these tiny fluctuations, are insignificant. They flash into existence and are gone, ruled by the probabilities of the quantum world. But what if one of them wasn't? What if by pure random chance one of these tiny energy bubbles, far smaller than an atom, didn't just collapse back into the foam? What if it had just the right properties? Just the right amount of borrowed energy that it survived? What if our entire universe is just one of these lucky fluctuations? A fluctuation that instead of vanishing began to grow. This leads to the how. How does a tiny probabilistic bubble survive and become a cosmos? The classical world gives us no answer. If you roll a small ball at a large hill, it needs energy to get to the top. If it doesn't have enough, it rolls back down, every time. But in the quantum world, the rules are different. That same ball, if it is a quantum particle, has a small but very real probability of not rolling over the hill at all. It can in a sense disappear from one side and reappear on the other. It tunnels through the barrier even though it classically doesn't have the energy to do so. This is called quantum tunneling. It happens all the time with electrons in our electronics. Now let's scale up that metaphor. What if the hill is the barrier between non-existence and existence? What if nothing, the quantum vacuum, is the state on one side and a real universe is the state on the other? The theory suggests that our universe did exactly this. It tunneled into existence. It was a probabilistic event. It didn't break the law of you can't get something from nothing, because in the quantum world that law doesn't fully apply. The universe in this view is the ultimate free lunch. It tunneled from a state of pure quantum potential into a state of real being. And this is where it connects so beautifully to our other grand idea, cosmic inflation. The universe that tunneled into existence wasn't the one we see, it was an infinitely small speck. But it was not stable. It was born into a state of tremendously high, unstable energy, a special kind of energy field that permeated it. This state had to decay, and its decay was the most violent and consequential event in our history. The consequence of this high energy state was a period of breathtaking exponential expansion. That initial quantum fluctuation was the trigger. The tunneling event was the spark. It's as if the universe was born as a tightly coiled spring, and the moment it became real, that spring unleashed. This unleashing was inflation. In a tiny fraction of a second, that microscopic quantum seed was stretched and stretched and stretched until it was macroscopic. This inflation did something crucial. It took that tiny, messy quantum bubble and flattened it. Any wild curvature, any wrinkles from its chaotic birth were stretched out, smoothed away. It's why when we look at the universe on the largest scales, it appears incredibly flat and remarkably uniform from one side to the other. This idea transforms our origin story. The Big Bang wasn't the beginning of everything, it was the moment that something, that initial inflated quantum seed, cooled down enough for its energy to transform into the particles, the matter, and the radiation that fill our cosmos today. The Big Bang was the start of the universe as we know it, but the true origin, the genesis event, was that tiny, silent, probabilistic leap from the foam, a fluctuation that decided to stay. It's a question that sits in the back of your mind, a simple, almost childish question that can unravel everything. Where did all this stuff come from? We look out at the cosmos, at the quadrillions of stars, the immense clouds of gas, the sheer weight of galaxies. We know that energy cannot be created or destroyed. That's the first rule of physics, the law of conservation of energy. So how did the universe begin? How do you get an entire cosmos bursting with energy and matter from nothing? It seems like the ultimate violation of the rules. To create the universe, you'd need an unimaginable amount of positive energy. Where did it come from? This is where a different kind of cosmic accounting comes into play, a concept most beautifully explained by the physicist Alexander Vilenkin. He suggested that we were only looking at one side of the ledger. Think of all the matter, all the light, all the stars, all the stuff in the universe as positive energy. It's the plus column. But the universe also has gravity. And gravity, it turns out, is the minus column. Think about it this way: to pull a planet away from its star, to overcome its gravity, you have to add energy. To lift a book off a table, you have to expend energy against gravity. This means that the gravitational field itself is a form of negative energy. It is an energy debt. Every time two objects are pulled together by gravity, they are in a state of negative energy relative to where they would be if they were infinitely far apart. Vilenkin's proposal, and that of others, is breathtakingly simple. What if the total energy of the universe is zero? What if the enormous positive energy of all the matter in the cosmos is perfectly balanced by the enormous negative energy of all the gravity holding it together? If this is true, then the universe didn't need a source of external energy to begin. It simply happened. It's a perfectly balanced equation. The total energy of nothing is zero, and the total energy of our entire universe might also be zero. This is what's famously known as the ultimate free lunch. The universe in this view is the result of a spontaneous fluctuation in the quantum vacuum. It's a burrowing from nothing. It didn't break the law of conservation of energy because in the end the net cost was zero. Imagine the vacuum of pre-creation not as an empty void but as a quantum foam, a sea of simmering potential where particles flash in and out of existence. In this state, a random wobble, a tiny quantum fluctuation could have occurred. This tiny fluctuation didn't just create a particle, it created a universe. It separated the positive matter and the negative gravity aspects of zero, and then critically inflation kicked in, stretching that tiny zero-cost bubble into the vast cosmos we see today. This idea is profound. It suggests that our universe didn't require a cause in the way we normally think of it. It could just be a natural, spontaneous, and perhaps even common event. And that leads us to the most staggering implication of all. If a random quantum event can create a universe from nothing, why would it only happen once? Quantum mechanics doesn't really do one-time events. It deals in probabilities. If the probability of something happening is not zero, then given enough time, or in this case a timeless quantum vacuum, it will happen. And if our theories of inflation and quantum physics are correct, it may be happening all the time. This is the multiverse. It's not a science fiction trope. For many physicists, it is the inevitable logical conclusion of our current best theories. If the quantum vacuum is a landscape of possibilities and If free lunch universes can pop into existence, then our universe is likely just one bubble in an infinite bubbling foam of other universes. Universes could be budding off constantly, each with slightly different laws of physics, different fundamental constants, maybe even to different dimensions. Some might expand and then collapse in a second. Some might be empty and sterile. And some, like ours, might have just the right combination of settings to allow stars, planets, and consciousness to emerge. This is where the science touches on something deeply philosophical. It can feel unsettling. If our existence is just the result of a random quantum wobble, if our universe is just one of an infinite number, what does that mean for us? It can make you feel small, accidental. It challenges the idea that our existence was intended. We are not the point of the cosmos. We are just a random, probabilistic outcome. It's a feeling of cosmic vertigo. We are here not because of a grand design, but because of a lucky roll of the cosmic dice. But perhaps that makes our existence even more precious. In a sea of infinite sterile possibilities, our bubble is one where the numbers came up right. Our meaning isn't handed to us from the outside. It's something that we must create for ourselves right here in this tiny, improbable pocket of the cosmos. Now this sounds like pure speculation. A zero-energy universe, a multiverse. It's easy to dismiss it, but we have a clue, a powerful piece of evidence that this isn't just a story. We can look back in time to the oldest light in the universe. We can look at the cosmic microwave background, the CMB. This is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. When we look at that snapshot, it is not perfectly uniform. It has tiny microscopic ripples in it, tiny variations in temperature. Those ripples, those are the seeds of all the galaxies we see today. They are the spots where gravity began to pull matter together, and what created those ripples. The best explanation we have is that they are the fossilized echoes of quantum fluctuations from the first trillionth of a second of the Big Bang, stretched by inflation to astrophysical size. Let that sink in. The largest structures in our universe, the great clusters of galaxies, grew from the smallest, most random wobbles of the quantum world. We have physical proof written across the entire sky that quantum mechanics shaped our cosmos. And if the quantum world could do that, if it could provide the seeds for our entire universe, is it really so hard to believe it could also create the seed itself? The CMB doesn't prove the multiverse, but it proves that the mechanism, the power of quantum fluctuations to shape reality on a cosmic scale, is very, very real. Let's return for a moment to the delicate vibrating world of string theory. It's a theory that requires us to imagine more than we can see, to accept that the fundamental reality of our world might be woven from threads of pure energy. But this theory doesn't just stop at tiny strings. It builds an entirely new vision of the cosmos itself, suggesting that the stage upon which our reality plays out is far grander and stranger than we ever thought. This vision suggests that our entire universe, everything we can see, every galaxy, every star, every atom exists on a vast three-dimensional membrane. Scientists call this a brain, which is just a shortened way of saying membrane. Think of it like this. Imagine our universe is a single vast sheet of paper. It has length and width, and for us it also has depth. This is our home. We can move forward, backward, left, right, up and down. But in this theory, our sheet of paper, our brain, is not alone. It is floating in a much larger, higher dimensional space, a space they call the bulk. We are in this view fundamentally creatures of the brain. We are stuck to it. The particles that make us the light we see, the forces that hold us together, they all live and move only along this membrane. We are like two-dimensional drawings on a piece of paper, completely unaware that there is a third dimension, up, just off the page. In this model, we are three-dimensional beings living on a three-dimensional brain floating in a cosmos that might have 4, 5, or even 10 dimensions of space. If this bulk exists, it seems unlikely that our brain would be the only one. The theory allows for the possibility of many brains existing side by side in this higher dimensional space. Imagine a stack of papers all floating parallel to one another, perhaps separated by only a tiny distance in that higher dimension. Each sheet is its own complete universe. Each one can have its own laws of physics, its own particles, its own history. These are parallel universes in the most literal sense. They might be less than a millimeter away from us right now, but we are completely isolated from them. We can't see them, we can't touch them, we can't travel to them. All the forces and particles of our bodies are glued to our own brain, just as the inhabitants of another brain are glued to theirs. We could pass through each other like ghosts, two separate realities coexisting in the same space, but in different dimensions. Now this might all sound like fascinating speculation, a kind of science fiction, and for a long time it was. But this model, this brain world idea, offers a stunningly elegant answer to one of the oldest and deepest mysteries in physics. Why is gravity so weak? Think about it. Gravity holds the planets in orbit and binds galaxies together, but on a small scale it's astonishingly feeble. A tiny fridge magnet can pick up a paperclip, defeating the entire gravitational pull of the planet Earth. Compared to the other forces of nature like electromagnetism or the nuclear forces, gravity is weaker by a factor of millions of millions. Brain theory says, what if gravity is the only force that isn't trapped on our brain? What if while light and matter and all the other forces are stuck to our sheet of paper, gravity is different? What if gravity is a property of the bulk itself? This would mean gravity can travel freely between all the brains and leak out into the higher dimensions. The gravity we feel in our universe would just be the tiny fraction that happens to stay with us. It's being spread thin, diluted across all those extra unseen dimensions. This leaky gravity would explain its weakness perfectly. It's not that gravity is inherently weak. It's that we're only feeling a tiny echo of its true strength. This idea of leaky gravity and parallel brains leads to an even more profound implication. It offers a completely new story for our origin, a new story for the Big Bang. This alternative is called the ekpyrotic model, a name which comes from an ancient Greek word meaning conflagration, or birth from fire. In this picture, the Big Bang wasn't the beginning of time. It wasn't an explosion that came from nothing. Instead, it was a physical event. It was a collision. Imagine two of these great parallel universe brains floating in the bulk. They are not static. They are moving, perhaps slowly drifting toward each other, pulled by the gravity that leaks between them. They drift closer and closer over unimaginable timescales until they collide. The kinetic energy of that cosmic crash, one universe-sized membrane slapping into another, is immense. That energy is instantly converted into a superheated firestorm of matter and energy. This, the ekpyrotic model says, is the event we call the Big Bang. The fire in conflagration. The hot, dense state from which our universe began its expansion was the moment of impact. And the beauty of this idea is that it avoids the most troubling part of the standard Big Bang, the singularity. The standard model says the universe began as a point of infinite density and infinite temperature. Physics breaks down at infinity. It's a sign that our theory is incomplete. But in the ekpyrotic model, there is no infinity. There is no magical point of creation from nothing. There is just a physical collision between two very large, very real objects. It's still a violent and awesome event, but it's one that physics can actually describe. It replaces a mathematical mystery with a physical process. This leads us full circle back to an idea we've touched on before, the cyclic universe. What if this collision wasn't the first and won't be the last? Imagine the brains not just colliding but bouncing. They crash together, ringing with the energy of a new universe. This ring is the expansion we see. The brains separate and our universe cools, forms galaxies and lives its long life. But perhaps the brains are still connected, maybe by a spring-like force from the bulk that slowly pulls them back together. After trillions of years, as our universe grows cold and dark, the brains are drawn together once more. They collide again. A new firestorm, a new Big Bang, and a new universe is born from the ashes of the old one. This is a universe that doesn't just begin once. It is a universe that is constantly reborn. Not a single bang, but an eternal rhythmic oscillation. A universe that breathes. It's natural after hearing all of this to feel a sense of unreality. Colliding sheets of reality. A universe born from a crash. A hidden bulk of higher dimensions. It feels like a myth. It feels like a story we would tell around a fire, not a scientific hypothesis. And that leads us to the most important, most necessary question in all of science. How would we know? It's a beautiful idea, but if we can't test it, it's just philosophy. It's just a mathematical game. And this is the biggest challenge. We are by definition trapped on our brain. If our universe is just one page in a vast higher dimensional book, we can't just peek over the edge and look at the next page. All the forces that make us the light we see with the matter, we are made of the electricity in our brains. It's all stuck to this page. It's like a drawing that can never ever leave the paper. It's drawn on. How can the two-dimensional drawing ever prove that a third dimension exists? It seems impossible, but there might be a loophole. There is one force in our universe that has always been different. It doesn't behave like the others. It's the force of gravity. Think about it. Gravity is unbelievably weak. Take a simple refrigerator magnet. That tiny piece of metal can pick up a paperclip, defeating the entire gravitational pull of the planet Earth. The electromagnetic force in that magnet is vastly more powerful than the gravity of a whole world. Why? Why is gravity the odd one out? Brain theory offers a stunning answer. What if gravity isn't weak at all? What if gravity is just as strong as all the other forces, but it's the only one that isn't stuck to our brain? What if gravity is the one thing that can leak? Imagine our brain is a giant sheet of glass. Light, matter and energy are all like beads of water sliding around on the surface stuck to it. But gravity is like a deep sound, a vibration that doesn't just travel on the glass, but travels through the glass and into the air all around it. In this model, the gravity we feel here on our brain is only a tiny fraction of its true strength. Most of it has leaked away, spreading out into the vast higher dimensional bulk. If this is true, it changes everything. It means gravity is our messenger. It's our one and only spy, our only connection to that larger reality. We can't see the bulk, but we might be able to feel it. So how do we listen to this messenger? We listen for tremors. We listen for gravitational waves. In the last few years, we have built incredible machines detectors that can sense a distortion in the fabric of space-time itself, a ripple smaller than the nucleus of an atom. We have already used them to hear the collision of black holes and neutron stars happening inside our own universe. We see the flash of light, and at the same moment we feel the thud of the gravity wave passing through us. But what if we heard the thud and saw nothing? Imagine our detectors register a massive event, a tremor so large it could only be two supermassive black holes crashing into each other. But we look, we point every telescope we have, visible light, X-ray, radio, gamma ray, at that spot in the sky, and there is absolutely nothing there. No light, no explosion, just a ghost signal, just the gravity wave. Where could it have come from? It could be the echo of an event from another brain. It could be the sound of two black holes crashing together on a parallel universe right next to ours in the bulk. We couldn't see them because their light is stuck to their brain, but their gravity isn't. Their gravity would ripple out across the tiny gap of that higher dimension and strike our brain like a bell. We would be quite literally hearing the echoes of another world. That is one way. There is another, perhaps even more profound. We can look for the bruise of our own birth. If our universe was created by a collision with another brain, it's unlikely that collision was perfectly neat and tidy. It would have been a cataclysmic, violent event. And that violence should have left a mark, an imprint on the very earliest moments of our cosmos. And we have a picture of that moment. We call it the cosmic microwave background, or the CMB. It is the oldest light in the universe, the afterglow of the Big Bang itself. It's a map of what the universe looked like when it was just a baby. This map is astonishingly uniform, but it has tiny, tiny differences in temperature, hot spots and cold spots that eventually grew into the galaxies and clusters we see today. Most of these spots are random, but what if they aren't all random? What if a brain collision left a specific pattern, a non-random signature like a fingerprint in the wet clay of creation? In fact, astronomers have found anomalies in this map. There is one area in particular known as the cold spot. It is a patch of the sky that is just a little too big and a little too cold to be easily explained by our standard theories. Most physicists believe it's just a random statistical fluke. But some wonder, could that be it? Could we be looking at the very point of impact the cosmic bruise left behind when another dimension struck ours and started the clock on our universe? This model, the brain collision model, also fundamentally changes our answer to the oldest question of all: what came before the Big Bang? In the standard model, this question makes no sense. It's like asking, what is north of the North Pole? Time itself and space itself began at the Big Bang. There was no before. But in the brain model, the question is suddenly valid. Before the Big Bang, before our Big Bang, there was the bulk. There were other brains. They were perhaps dark, cold and empty, drifting in that higher dimensional space for eons. Time did not begin with us. It was already flowing in that vast hidden ocean. Our beginning was just a local event. It was the moment our page was struck, the moment the fire was lit. But the book was already there. Time is older than our universe. This leads to one last dizzying thought. If there are other brains, are they like ours? Do they have the same laws of physics? The theories that underpin all of this string theory, M theory, suggest that the answer is no. They suggest that there isn't just one way to build a universe. There are possibilities. Perhaps 10 to the power of 500 possibilities. A number so large it makes your head spin. It's an ocean of potential universes, each with different settings. This is called the string landscape. Imagine a cosmic foam with countless bubbles. Each bubble is a brane universe. In one bubble, gravity is strong and life is crushed. In another, electrons are too heavy and stars can't ignite. In another, there is no light at all. Most of these bubbles are sterile, dead, collapsing in on themselves in an instant. But in this infinite foam, by pure dumb luck, a few bubbles would have the exact right settings, the exact weakness of gravity, the exact mass of the electron, the exact strength of the forces needed for stars to burn for billions of years, for planets to form, for chemistry to become complex, for life to crawl out of the oceans and eventually look up at the sky and wonder where it came from. We aren't living in the only universe, we are simply living in one of the ones that worked. This is where physics and philosophy meet. We are searching, we are listening for the tremors of a parallel world. We are scanning that ancient fossil light for the scar of our own creation. We are no longer just guessing, we are actively hunting for the echoes of another dimension. So far our journey has been guided by a powerful, elegant map of the cosmos, Einstein's general relativity. It has guided us through expanding space, bending light, and the slow dance of galaxies. But this beautiful map has a flaw. At the two most extreme places in the universe, the very center of a black hole and the very beginning of the Big Bang, the map simply stops. The equations break, the numbers go to infinity. In physics, infinity is not a number, it's a confession. It's the universe telling us your theory doesn't work here. This point of failure, this spot where our understanding collapses, is the singularity. For a century we've treated it as a starting point, but it isn't. It's a wall. And to get past that wall, we need a new theory. We need something that can bridge the two great pillars of physics. Think of it this way. We have two separate rulebooks for the universe. The first is General Relativity, Einstein's book. It describes the big, the heavy, and the smooth. It's the law of planets, stars, and the graceful curved fabric of space-time. This second rulebook is quantum mechanics. This is the law of the very, very small atoms, electrons, photons. It is a world that is not smooth at all. It is fuzzy, uncertain, and quantized, meaning it comes in lumpy individual packets. These two rulebooks are brilliant, but they don't speak the same language. General relativity describes a smooth-flowing river. Quantum mechanics describes that river as being made of countless individual water molecules. They are both correct, but they are different descriptions. The problem is the Big Bang was a place where both sets of rules had to apply. It was an event of unimaginable mass and energy, the domain of general relativity crushed into a space smaller than an atom, the domain of quantum mechanics. To understand the origin, we need a single unified theory that can describe both the river and the molecules. We need a theory of quantum gravity. We don't have a final proven theory yet, but we have two extraordinary candidates, two breathtaking ideas that suggest what the ultimate reality might look like. The first contender is called loop quantum gravity. This theory is a direct attempt to quantize space itself. It asks a simple question: what is space? We tend to think of it as an empty, smooth, continuous backdrop, like a blank sheet of paper on which the universe is drawn. Loop quantum gravity says this is wrong. It says that if you could zoom in way, way down, far smaller than any particle, you would find that space is not smooth at all. It's a fabric. It is woven from tiny, discrete, fundamental loops of gravitational energy. Space itself is built from something like a t-shirt is woven from threads. This means that space is not infinitely divisible. There is a smallest possible area, a quantum of space. You cannot have half a quantum of space, just as you cannot have half a photon of light. This pixelated structure of reality changes everything. Most importantly, it solves the singularity problem. If space is made of indivisible pixels, then you can't crush the universe down to an infinitely small point. You can only crush it down until it hits the fundamental grain of the fabric. At that point, the quantum nature of gravity, which is normally incredibly weak, becomes the most powerful force in the universe. It creates an immense push, a repulsive force that stops the collapse. In this picture, the Big Bang was not a beginning from nothing, it was a big bounce. Our universe, this theory suggests, may have existed before. It may have been a previous universe that expanded, slowed down, and then collapsed back on itself. It rushed toward a singularity, but it never reached it. Instead, it hit this quantum floor, this point of maximum density, and bounced. The Big Bang was the moment of that rebound, the beginning of our expansion, like a great cosmic exhale. The singularity, the place where our math broke, is gone. It's replaced by a bridge. That is one beautiful idea. The other is perhaps even more famous. It is called string theory. String theory starts from a different place. It doesn't try to quantize space first, it tries to quantize matter. It looks at the dazzling variety of particles in the universe, electrons, quarks, photons, neutrinos, and asks why so many. The answer it proposes is music. String theory suggests that if you could zoom in on an electron, you wouldn't find a point. You would find a tiny vibrating loop of energy, a string. And if you looked at a photon, you'd find another string, and a quark another string. They're all at their core the exact same thing. So why do they look so different to us? Why does one behave like matter and one like light? Because they are vibrating at different frequencies. Think of a single guitar string. Pluck it one way and it plays a C, pluck it another way it plays a G, pluck it a third way it plays an E. It's all the same string, but it produces different notes. String theory says the universe is exactly this. An electron is just a string vibrating in one note. A photon is the same string vibrating in another note. All the particles and forces we see are not fundamental things at all. They are just the different harmonies of a single fundamental cosmic string. This is an idea of ultimate elegance. It unites everything, matter, light, even gravity, into one single concept. But it comes with a price. For the math to work, string theory requires that the universe has more dimensions than the 3 we see. Perhaps 10 or 11 dimensions of space, with most of them curled up incredibly small, hidden from our senses. This weirdness, however, leads to profound consequences. One is a concept called T-duality, a mind-bending symmetry. It suggests that if you take one of these extra dimensions and make it very, very small, smaller than the string itself, the physics becomes exactly the same as if that dimension were very, very large. The universe at this level cannot tell the difference between the infinitely small and the infinitely large. This could also explain why our universe is the way it is. One idea, string gas cosmology, imagines the early universe as a hot, dense gas of these strings. The strings were wrapped around these tiny curled-up dimensions. As the universe tried to expand, the strings stuck together, preventing those extra dimensions from growing. But 3 of the dimensions were not wrapped. They were free. And so they were the only ones that expanded, blossoming into the vast 3-dimensional cosmos we call home. The strings themselves may have chosen the shape of our reality. So where does that leave us? With 2 grand competing visions. Are we living in a woven universe built from discrete loops of space, or are we living in a musical universe made of the vibrating notes of tiny strings? We don't know. Both ideas are still on the frontiers of mathematics, just beyond the reach of our current experiments. But in their search, they have both erased the infinity that haunted us. They have both replaced the singularity, that the wall of broken math, with a beautiful new idea. One shows us a bounce, the other shows us a symphony. We have travelled across the vast cosmic web, witnessing the dance of galaxies over billions of years. We have also looked inward into the strange quantum world that governs the very small. Now we must push the boundaries of our imagination, shrinking down past the atom, past the nucleus, beyond the quarks, to a scale so small that our very concepts of space and place begin to dissolve. We have arrived at the Planck scale, the smallest possible unit of measurement in the universe. Here the physicist John Wheeler suggested that reality is not smooth and continuous. Instead, if we could zoom into this impossible degree, we would find what he called quantum foam. Imagine you are looking at the ocean from a very high airplane. It appears perfectly smooth, a flat blue sheet. As you get closer, you see waves. Closer still, you see the chaotic spray, the chop and the bubbles. The smoothness was just an illusion of distance. Wheeler proposed that space-time itself is like this. At our scale, it looks smooth and reliable, but at the Planck scale, it is the boiling, chaotic, seething cauldron of energy. It is sizzling with activity. In this foam, the laws of physics are not fixed. Tiny virtual particles pop into and out of existence in an instant. Tiny microscopic wormholes might be tearing and repairing themselves, connecting one part of the foam to another. Geometry itself is fluctuating. This is not a still place. It is a world of pure potential where the very fabric of reality is being constantly woven and unwoven moment by moment. This is the fundamental pixel size of our universe. This idea that reality is grainy and chaotic at the bottom connects to one of the most profound and mind-bending concepts in all of theoretical physics, the holographic principle. This principle was born from studying black holes. A mystery puzzled physicists for decades. When something falls into a black hole, what happens to its information? Information in physics is the unique description of an object. The laws of quantum mechanics say that information can never be truly destroyed. but a black hole seems to crush everything to a single point. The solution was a breakthrough. It appears the information doesn't fall into the center. Instead, all the information about everything that has ever fallen into the black hole, every star, every particle, is perfectly encoded on the surface of the black hole, the two-dimensional event horizon. It's like the object is smeared across the boundary. This led Hooft and Susskind to ask a radical question: if a three-dimensional object like a star can be fully described by a two-dimensional surface, the event horizon. Could this be true for everything? This is the holographic principle. It suggests that all the information contained within a volume of space, this room, this planet, this entire galaxy, can be perfectly encoded on the boundary, the surface of that space. The implication is staggering. It suggests that our reality, the three-dimensional world we experience with its depth, height, and width, might be a projection. We might be a hologram. The real data that makes up you, me, and the stars is actually written on some vast, distant, flat, two-dimensional surface that forms the boundary of our cosmos. What we experience as gravity might not be a fundamental force at all. It might just be the thermodynamic effect of this information moving and organizing on that distant boundary. What we experience as moving through space might just be the holographic image shifting. This concept connects the very smallest, the quantum foam, the pixels of space-time, with the very largest, the boundary of the entire universe, the screen on which the hologram is projected. This leads us to a new way of thinking about the most important event of all, the beginning. We call it the Big Bang. This word gives us the images of an explosion, a cosmic firecracker going off in the middle of an empty, dark room. But this metaphor is deeply wrong. There was no room for it to explode in. The Big Bang was the creation of the room. It was the birth of space and time itself. So we need a better metaphor. Let's stop thinking of it as an explosion and start thinking of it as a phase transition. A phase transition is something you see every day. Think about water. Water has three phases: solid, ice, liquid water, and gas steam. They're all the same molecule, 2 parts hydrogen, 1 part oxygen, but they behave completely differently based on their energy levels. Ice is a crystal. It is highly ordered structures and has a defined geometry. Liquid water is less ordered. It flows and takes the shape of its container. Steam is completely chaotic, a high-energy gas that expands to fill any volume. Now imagine this process in reverse. Imagine you have a cloud of incredibly hot, chaotic steam. As it cools, it reaches a critical point and condenses into liquid. If it cools further, it reaches at another critical point and freezes into a highly ordered, structured ice crystal. Perhaps the Big Bang was not an explosion. Perhaps it was a condensation. Let's call the earliest moment of the universe a pre-geometric state. It was like the steam. It was a chaotic, dimensionless foam of pure energy. There was no space or time as we know them. There were no laws of physics. It was a state of pure hot potential. Then the universe began to expand and cool. It reached a critical temperature, and in a fraction of a second it froze. This moment is what some physicists call geometrogenesis, the birth of geometry. Like steam condensing into a structured ice crystal, that formless pre-geometric foam suddenly crystallized into the reality we know. Space and time froze into existence. The laws of physics, like the rules that govern the shape of crystal, locked into place. The universe we recognize with its 3 dimensions of space and 1 of time was born. This phase transition model solves one of the greatest mysteries of cosmology. Why did our universe begin in such a perfect, orderly and low entropy state? An explosion creates a mess. It creates disorder, high entropy. If the Big Bang were an explosion, it should have created a lumpy, chaotic, disorganized universe. But we see the opposite. The early universe was incredibly uniform and smooth. A phase transition, however, naturally creates order. When water freezes, the chaotic random molecules of the liquid snap into the perfect repeating ordered pattern of an ice crystal. The chaos of the hot state naturally gives way to the order of the cold state. So the Big Bang may not have been a bang at all. It may have been the moment the cosmic water froze. It was the moment of crystallization when the rules of our reality were set, and the stage was prepared for the long, slow evolution of stars, galaxies, and eventually for us, the part of the crystal that woke up and is now trying to understand the frost. We have spoken of time as a dimension, as a river, as a relative and flexible thing. But now we must face the most profound, the most unsettling, and perhaps the most beautiful idea of all. What if time doesn't exist? What if the flow of time, the very thing that defines our lives, is an illusion? This isn't just idle philosophy. It is a possibility that emerges from the deepest roots of our physics. We are now considering time not just as a part of the universe, but as a feature that emerges from a deeper timeless reality, much like the patterns of a flock of birds emerge from the simple rules of each individual bird. Let us first consider a world without time. The physicist Julian Barbour has championed a radical idea that the universe consists only of nows. Imagine a vast landscape of every possible arrangement of everything in the universe. Every single moment is a complete self-contained snapshot. You, reading this in this very specific arrangement of atoms, is one now. You, a second later, is a different now. In this view, there is no river carrying us from one moment to the next. There is only a collection of these static moments. So why then do we feel time passing? Why do we have memories of a past? Barber's answer is that our memories are not records of a place we were, but are simply patterns, physical structures encoded within the current now. Your brain in this present moment contains configurations of neurons that correspond to what you call yesterday. You're not remembering the past. You're observing a feature of the present. The feeling of flow, the sense of passage, is a psychological illusion created by the brain processing these static records in sequence. The universe is like a single magnificent book, but we are reading it one page at a time, convinced that the pages are being created as we go. In reality, all the pages exist simultaneously. This idea, as strange as it sounds, finds support in one of the most mysterious equations in all of physics, the Wheeler-DeWitt equation. This is not an equation you can solve easily. It is a profound theoretical statement. It was born from the attempt to merge our two greatest theories, general relativity, which describes the vast universe of gravity and space-time, and quantum mechanics, which describes the bizarre world of atoms and particles. When you try to write an equation that treats the entire universe as one single quantum object, something extraordinary happens. The variable for time, the letter t, that is present in almost every other physical equation, simply vanishes. The equation describes a universe that is in a quantum sense static. It doesn't evolve in time, it just is. This block universe concept, where past, present and future all exist together, is a direct consequence of trying to apply our most fundamental rules to reality as a whole. According to this, the universe isn't a story that is unfolding, it's a sculpture that we are just experiencing from one perspective. The flow we perceive is just our consciousness tracing a path through this timeless static reality. If this is true, if the fundamental reality is timeless, then where does our everyday experience of change come from? A powerful new idea suggests that time emerges from quantum entanglement. We've spoken of entanglement before, that spooky action at a distance where two particles remain connected, their fates intertwined no matter how far apart they are. What if time is not a fundamental background but a relationship? Imagine the universe is in this timeless state described by the Wheeler-DeWitt equation. Now imagine splitting it into two parts, a clock and the rest of the universe, which includes us. These two parts are entangled. While the total universe is static, the relationship between the clock and the rest of the universe is not. As the clock part changes its state, say our hand ticks forward, the rest of the universe part also changes its state because they are linked. We, as part of the rest of the universe, perceive this correlated change as the passage of time. In this view, time is not an absolute external thing. Time is the measure of entanglement. It is the dance of correlations between the parts of the whole. A universe with no entanglement would be a universe with no time. This elegantly explains why we perceive time even if the universe as a whole is timeless. We are not outside observers, we are part of the system entangled with our surroundings, and our perception of time is a direct result of that entanglement. This connects directly back to our old friend entropy. Remember we said the arrow of time points in the direction of increasing disorder, increasing entropy. This new idea deepens that understanding. The growth of entanglement is the growth of entropy. A system with low entropy is simple with few connections. A system with high entropy is complex with many parts entangled in intricate ways. The past, therefore, is simply a state of lower entanglement, and the future is a state of higher entanglement. The arrow of time is simply the universe's natural tendency to become more and more entangled with itself, to spread correlations and information throughout its parts. And this brings us to information. It may be that time at its very core is about information. The passage of time is the processing of information. A memory is information stored in the present. A calculation is the processing of information. Entanglement is shared information between systems. The laws of physics themselves can be reimagined not as laws of motion, but as laws governing how information is stored, moved and transformed. This is why black holes are such a puzzle. The black hole information paradox asks what happens to the information of a particle that falls in. Quantum mechanics insists that information can never be truly destroyed. General relativity suggests it is lost forever behind the event horizon. This clash is a sign that our concepts of gravity, quantum mechanics, and time are incomplete. Perhaps the solution is that information is fundamental, and time itself is a way of accounting for it. To solve the paradox, we may have to accept that our very notion of a moment in time breaks down at the edge of a black hole. So what are the consequences of all this? If time is not a fundamental river, but an emergent property, a local complex and relational phenomenon, like wetness or life, it changes everything. It means time might not be universal. It might flow at different rates or in different ways in other parts of the cosmos. It means time itself had a beginning not just in the Big Bang, but in the moment the universe first developed these complex relationships. And it leads to a final staggering thought. What happens in the far, far, far future? We spoke of the heat death of the universe, a state of maximum entropy where everything is in perfect equilibrium. In this future, all the stars have burned out, all black holes have evaporated, and all particles are spread thinly and uniformly through a cold, dark, endless space. In this state of perfect balance, there is no more room for entanglement to grow. There is no more information to be processed. There is no more complexity to be built. If time is the measure of increasing entropy, what happens when entropy can increase no more? The implication is as chilling as it is profound. Time itself may stop. The flow we experience, the product of change and entanglement, would simply cease. The universe would return to that timeless static state described by the Wheeler-DeWitt equation. A silent, unchanging eternal. Now, the grand story of the cosmos, which began with a burst of energy and evolved through eons of change, would find its final state in a perfect, quiet, timeless end. The river of time, which has carved the entire landscape of reality, would finally, after trillions upon trillions of years, flow into a boundless, changeless ocean, and all would be still. We have travelled from the quantum foam to the edge of the cosmic horizon, from the birth of stars to the mystery of the void. And now we arrive at the final question, the one that underlies all others. How did it all begin? For so long, our story of the cosmos began with a paradox, a singularity, an infinitely hot, infinitely dense point that marked the beginning of time, but which was in reality a point where our equations, our physics, and our understanding simply broke. It was a wall. But what if that wall isn't a feature of the universe, but a failure of our perspective? This brings us to one of the most profound and philosophically complete ideas in modern physics, the no-boundary proposal developed by Stephen Hawking and James Hartle. It is a concept that dares to suggest that the question we've been asking, what happened before the Big Bang, might be the wrong question entirely. It's a proposal that offers a universe that is elegant, finite, and yet utterly complete with no beginning and no end, a universe that is entirely self-contained. To understand this, we must first revisit the very nature of time. The proposal's core relies on a fascinating mathematical tool, a concept known as imaginary time. This isn't make-believe time, rather it is a mathematical rotation. Think of our familiar real time as a line, a river flowing in one direction creating the before and after that defines our entire existence. But in the extreme conditions of the very early universe before time, as we know it even existed, quantum mechanics takes over. In this quantum realm, Hartley and Hawking applied a mathematical trick transforming this real time into imaginary time. What does this do? It magically changes the behavior of time. Under this mathematical rotation, time stops behaving like a one-way river and starts behaving just like another dimension of space. It becomes the direction, like up or down or left or right. This one technical change has a staggering consequence. It allows us to smooth out the singularity. Imagine the universe as the surface of a sphere like the Earth. If you are standing at the North Pole, there is no north of the North Pole. Every direction you point is south. The North Pole is a point on the globe, but it's not a boundary or an edge. The surface of the Earth is finite, but you can walk on it forever without falling off. This is what imaginary time does to the Big Bang. The beginning of the universe is no longer a sharp, violent point, the singularity, but rather a smooth, curved cap, like the North Pole of our sphere. Time and space merge into a seamless four-dimensional geometry. There is no edge, there is no boundary. If the universe has no boundary, how did it become the specific universe we see today? This is where the idea of a path integral or a sum over histories comes in. In the quantum world, a particle doesn't just take one path from point A to point B, it explores all possible paths at once. Its final observed path is just the sum, the average of all these possibilities. The Hartley-Hawking proposal to Yale's this idea up to the entire cosmos. In that initial timeless phase, in that smooth geometric cap of imaginary time, the universe didn't have the one single history. It contained every possible history, every possible shape, every possible set of laws, every possible way a universe could be, all existed at once in a state of pure quantum probability. Our universe, the one we inhabit, is simply the history that emerged from that sum as the most probable. We are the result of a grand cosmic average of all the things that could have been. But we do not live in that fuzzy, probabilistic imaginary time. We live in real time. We remember the past and we anticipate the future. So what caused the switch? What turned that timeless spatial geometry into the flowing river of time we experience? The answer may lie in a process called quantum decoherence. As this tiny seed-like universe, which was just a set of potentials, began to expand, it effectively observed itself. The different possible histories began to interact, to interfere with each other and to separate. The quantum fuzziness collapsed. The superposition of all possible universes resolved into one specific classical universe. This process, this decoherence, is the birth of time itself, the imaginary time which was just another direction rotated and froze into the real time we know. The arrow of time, the sequence of cause and effect, the very concept of a past and future, all of these are emergent properties. They are the record of the moment the universe chose its history and became real. The philosophical implications of this are staggering, perhaps the most profound in all of science. If the universe is a finite no-boundary geometry, it is completely self-contained. It doesn't need a first cause. It doesn't need an external force to set it in motion. The unmoved mover that philosophers have sought for millennia is no longer required. The universe simply is, and its existence is its own reason. It is a system that explains itself from within. It is a loop, a geometry of existence that contains its own origin, and so we end our journey. The cosmos in this beautiful and elegant picture did not begin with a bang, a violent external explosion that shattered an empty void. It began instead as a breath. It was a quiet, smooth and inevitable transition from a state of pure timeless mathematical possibility into a state of unfolding dynamic physical reality. It was a shift from being possible to becoming actual. The universe is not just a story, it is a geometry, a perfect self-contained shape that simply and beautifully is.